All right, let's jump straight into this explainer. Today, we are dissecting a structure that wasn't just built to stand, it was built to wage an all-out war with the planet's most extreme forces. This is a masterclass in physics and high-stakes survival. The Akashi Kaikyō Bridge in Japan isn't just a bridge, it's a monumental declaration of human defiance against some of the most violent natural phenomena on Earth.
Building the world's most impossible bridge in one of the most volatile environments on Earth. Think about that for a second. When you build in a location plagued by typhoons, aggressive ocean currents, and hyperactive fault lines, you aren't just designing a roadway. You are quite literally forging armor against absolute catastrophe. Every single component here must anticipate total disaster.
Section 1. Conquering the raging currents. This battle begins at the absolute bottom, where the Foundation had to defeat the hostile raging sea currents of the Akashi Strait. To pull this off, engineers relied on massive hollow steel cylinders called caissons. We're talking colossal structures, 80 meters wide and 65 meters deep. Prefabricated on land, these monsters were carefully towed out into those churning, raging currents and sunk to the seafloor with absolute millimeter precision.
But look, dropping a massive steel cylinder into the ocean, that's really only half the battle. To stop those violent currents from simply scouring the seabed and washing the entire foundation away, they actually created a revolutionary, custom-designed underwater concrete. It's engineered specifically to solidify and stay perfectly intact without dissolving in that highly corrosive salt water, locking the bridge to the bedrock like an unshakable anchor.
Moving to Section 2, defeating aeroelastic flutter. Now, as the structure rises above the water, it faces a terrifying new enemy, the sky itself.
The bridge had to be designed to survive relentless typhoon-force winds of 180 miles per hour without tearing itself apart. I mean, just imagine the sheer kinetic energy of a Category 5 hurricane relentlessly hammering a structure suspended that high up in the air.
So what do? Engineers completely abandoned a solid concrete deck in favor of a complex steel truss system. A traditional solid concrete deck is super vulnerable to destructive aerodynamic lift. It would act like a giant airplane wing. So instead, they engineered a triangular steel lattice cage right underneath the road.
And this is crucial because of aeroelastic flutter. These are the destructive, resonant lift forces that notoriously tore the Tacoma Narrows Bridge apart in the 1940s. By letting that 180-mile-per-hour wind blow right through the triangular lattice, the kinetic energy simply bleeds straight through the steel skeleton, entirely defeating the threat.
Section 3. The Internal Balancing Act. Because stopping the deck from lifting just wasn't enough, the immense towers needed to fight their own fierce battle against extreme sway. These colossal steel towers reach 297 meters into the sky. That makes them almost as tall as the Eiffel Tower. And at that height, acting as a giant lever, they are highly susceptible to wind and seismic sway. Even the slightest vibration at the base can multiply into a structurally fatal sway at the top. To survive, each tower houses a high-tech robotic immune system. Step 1. The wind pushes that 297-meter tower to the left. Step 2. Hypersensitive computer sensors instantly trigger. And Step 3. 20 heavy, computer-controlled, tuned mass dampers simultaneously shift to the right. It is literally a high-tech internal balancing act. They violently throw their immense weight against the wind, perfectly neutralizing the kinetic energy and fighting off typhoons split second by split second.
Section 4. The 1995 Kobe earthquake. The advanced dampeners and trusses were flawless against the sky, but absolutely nothing could prepare this incomplete bridge for the terror that was about to detonate beneath it.
January 17, 1995. The catastrophic 6.9 magnitude Great Hanshin earthquake violently ruptures the earth right near the site. The massive towers were fully built, and the main load-bearing cables were actively being strung. The bridge was completely exposed, caught right in the middle of construction during one of the most destructive quakes in Japanese history.
And in a truly terrifying display of planetary power, the tectonic plates shifted so violently they dragged those colossal towers an entire meter further apart from each other. Mid-construction, imagine the unfathomable force required to rip the actual crust of the Earth apart, taking a half-finished megastructure with it. The entire geometric calculus was shattered. Having its anchor points violently yanked a full meter apart under immense tensile stress should have completely snapped the bridge into the ocean. But it didn't fall. The bridge's massive flexible margins actually absorbed the lethal shock. Because it was designed to bend rather than break, it survived.
And instead of abandoning the ruins, engineers went right back to the drawing board. They systematically recalculated the impossibly complex math on the fly and adapted the design by adding exactly 1 extra meter of roadway to bridge the new earth-shattering gap. Incredible, right?
Finally, Section 5, the unbreakable steel threads. Having survived a direct hit from a tectonic rupture mid-construction, the final step was locking this immense survivor together under a continuous tensile load.
To span this newly stretched tectonic distance, engineers developed a brand new galvanized steel wire so unbelievably strong that a single strand, just 5 millimeters thick, can support the weight of 3 family cars. Think about that density of strength. 5 millimeters. It's practically the thickness of heavy yarn, yet it holds thousands of pounds. By bundling tens of thousands of these unbreakable, ultra-high tensile 5mm wires together, they finally locked those newly separated 297-meter towers into their permanent post-earthquake positions. These massive cables carry the immense, continuous weight of the whole shebang, the truss, the roadway, and every single vehicle crossing the strait.
So, after watching extreme engineering defeat 180-mile-per-hour winds and a 6.9 magnitude tectonic shift right in the middle of construction, what does this triumph mean for the ultimate future of human endurance against nature? Think about the sheer scale of adapting to a tectonic shift in real time. It proves that with enough ingenuity, we aren't just at the mercy of a violent planet. We can calculate, adapt, and endure. So, looking at this triumph of physics, what impossible frontiers will we conquer next?